Okay, so today we're going to look at the theoretical probability and what that is. So our learning intention is to gain the knowledge of what theoretical probability is and how to calculate it. So we'll be successful if we know what it means, theoretical probability, if you can correctly determine the possible number of outcomes, and if you can correctly calculate the theoretical probability of a specific event or experiment or outcome. Okay. We've probably been doing theoretical probability for ever since primary school. It is basically based on reasoning, and it's written as a ratio of the number of favorable outcomes over the total number of outcomes. And there's the formula. The probability of an event occurring is the number of favorable outcomes of the net favorable event over the total sample space. So, for example, flipping a coin, the probability of flipping a coin and landing on heads there are two outcomes, and landing on head is one. So that's what we mean by theoretical probability. The reasoning of the outcomes over the sample space. Okay. Some things that we need to be aware of. The theoretical probability means in reality, if I was to flip a coin, I wouldn't necessarily have a chance on 1 on 2. I might, if I did it quite often, I might get head, then the head, then a head, then I might get a tail and a head. So and if I did all that, the relative probability of that wouldn't equal a half. But the more times I do it would eventually mean, so the larger number of trials, the closer the result will become equal to the theoretical probability. So the more times I flip a coin means I will have the probability of getting landing on the head to be equal to a half. Okay. It's also important to understand what mutually exclusive events are. And these are events that cannot occur at the same time. So, for example, if I was to roll a dice, I can't land on a 5 and a 6 at the same time because there's only one die. If I was picking a card that had the letters of the alphabet, right, it would be the possibility of picking up a vowel is mutually exclusive to picking up a consonant. Yeah. We can also say it's also called the disjointed set. So when we're talking about Venn diagrams, it's the disjointed set. The sets are separated and there's no overlap. So the example that I have here is of set A. This is the whole set of the letters of the alphabet. I have a subset in that of V, which is the vowels, and a subset of C, which is the consonants. They're disjointed and so therefore they're mutually exclusive. It's impossible to pick up a vowel that's also a consonant. Yeah. We say that the probability of the intersection, so the probability of A and B, so the overlapping part, is equal to the empty set, is the sample space of nothing, or that simple 0 with a mark through it, and then we call that the empty set. Okay. The addition rule for mutually exclusive events, yeah. So if I wanted the probability of the union of A or B, well, that's the probability of A occurring plus the probability of B occurring. Because if I add those two together, I should get a probability of one, the probability of something occurring. Another thing that we need to understand is what are complementary events. And these are, this is the event not occurring. So, and we usually write it with a line above the probability. So the probability of E not occurring is going to be 1 minus the probability of E actually occurring. Because we understand that probability of something has to always equal to 1. So if I subtract it from happening, then it will give me what's not happening. Or alternatively, the probability of E happening plus the probability of E not happening has to equal to 1. Okay, let's do some examples. Okay, a pack of cards contains 52 playing cards. Okay, calculate the theoretical probability that the card drawn would be red. Okay, well there are 4 suits. There are 4 suits. Two of them are red, which are the hearts and diamonds. Each suit has 13 cards that range from ace to 10, and then jack, queen, and king. So I can do it as 26 over 52, as in 13 hearts and 13 diamonds, which simplifies to 2 red suits out of 4, which simplifies down to a half. So the probability of drawing a red card would be a half. So the probability in this situation now to draw a picture card, so the probability of drawing a picture card, okay, well, there's 3 per suit, which are the jack, queen, and king. So in this situation, there'd be 3 out of 13. As there's 13 cards in a suit, and 3 of them are picture cards. What's the probability the card drawn would not be a picture card? So I write the probability of picture card with a line above it, because that stands for not occurring. Okay, well then that's going to be the opposite of it occurring. So that's the same as 1 minus 3 over 13, which is 10 over 13. So the probability of picking a card that's not a picture card will be 10 over 13. The probability of the card drawn would be the 2 of hearts. Okay, well then that's 1 card out of the whole 52 that we have. And here we've got the probability of it not being the 2 of hearts. Well, then that's going to be 1 minus 1 over 52, which is going to be 51 over 52. Okay. And now, last one, the card drawn will be a prime number. Okay, so the prime numbers that we have 2, 3, 5, 7, that's it. Okay, so the probability that's going to be a prime number remember that each suit has 13 cards. We've got 1, 2, 3, 4 numbers, so it's going to be 4 out of 13. Obviously with probability, theoretical probability, it's important to know your playing cards. It's important to know things like your prime numbers, the difference between vowels and consonants, because you'll find a lot of questions are based on those common things, and dies. Okay, here's an example using a Venn diagram. So we have the set of A being all the odd numbers from 1 to 20. We have the set of B being all the even numbers, and I have this intersection where they're basically factors of 20. Yeah, so this A and B is factors of 20. So we want to find the probability of A. So of picking an odd number from 1 to 20. So now there are obviously 20 possible solutions, and we're looking at just the odd ones, which is 10 of them. So it's going to be a half. Obviously, the probability of A not occurring is going to be 1 minus a half, which is still a half. Obviously, the probability of it being even is going to be the same. and not even is going to be the same. Yeah. We want the probability of A union B. Okay. So what we mean by that is the probability of A plus the probability of B minus the intersection, because you don't want to add those together. But the problem is that this jointed here was not the best joint. So in this case, the probability of the union of picking a number between 1 and 20 is obviously 1. Yeah. The probability of not picking the number from 1 to 20 will be 0, impossible. But the intersection, so the problem is I've written the anything that was odd here and anything, so odd here and anything even here, but obviously this 1 and 5 doesn't belong to B, group B. So we still have 2, 4, 6 out of the 20 numbers. So that's 3 over 10. And the probability of not that occurring would obviously be minus from 1, so it'll be 7 over 10. Okay. Okay, thank you very much.